Hi there! This is the fifth part of the tutorial how to play a video on Arduino Uno. In the last episode we already showed you how to play a 20 frames per second video. However, our final goal is to get video along with audio. In this part we will show you how to play a 16-bit 20 kilosamples per second audio using the Arduino Uno. Let's go for the next hack! The aim of this episode is to play a 16-bit single-channel 20 kilosamples per second audio file. This project can be modified with minor hardware and software changes to have a stereo 8-bit channel playback. Like we said in the previous episode, the ATmega328P has not enough computing power to perform on-the-fly decoding of compressed audio. Therefore, we will use uncompressed audio files. Storing and playing audio is usually accomplished by using a technique called pulse code modulation, or PCM. The signal we want to store is sampled at regular intervals. The sampling frequency is called also sample rate. Now, instead of our audio signal, we have a series of pulses, hence the name pulse code modulation. Each of these pulses cannot be stored yet in a digital form, as they must be quantized. In fact, once we choose the number of bits per sample, we determine the number of levels that each sample can assume. For instance, using 3 bits per sample, we have 8 levels, which we marked with the horizontal dashed lines. For each sample, we look at the level that best approximates the original value. This operation is performed by the ADC, analog to digital converter. For each quantized sample, we store in the file the number of the corresponding level. However, we want to play a file. Therefore, these operations were already performed when the audio file was created. To play this file, we must perform the opposite operation, that is, the demodulation. For each sample, we generate a voltage which is kept constant for the whole sample time. After that sample time, a new voltage is generated, corresponding to the next sample value. This repeats as long as we play our audio. The achieved signal is a series of steps that approximates the original value. A low-pass filter is inserted to eliminate such abrupt steps between samples. By increasing the number of bits and the sample rate, the approximation will be improved. Therefore, we will achieve a better audio quality. Okay, now we know something about PCM. Can we start producing our audio using the Arduino Uno? Not yet. The Arduino Uno has no digital to analog converters. Therefore, we must use a technique called pulse width modulation. Yes, another modulation. A pulse width modulator, or PWM, consists of a ramp wave generator and a comparator. The signal to be modulated must be slow, so that we can consider it constant, at least during a single ramp period. When the ramp value is smaller than the signal, the output will be high. Once the ramp value is higher than the signal, the output goes low. What we achieve is a rectangular wave with a duty cycle proportional to the input voltage. Therefore, we associate the duty cycle to the voltage value of the input signal. After we created the PWM signal, we use a filter to get its average value. The filter actually performs the demodulation. In fact, the average value of a rectangular wave is proportional to its duty cycle, which, in turn, is proportional to the original sample value. In our case, we don't have an analog input signal, but a series of numbers. What we perform is a digital PWM. To generate the rectangular wave with the desired duty cycle, we just need to use the PWM function of our microcontroller. It consists of an up-counting timer, which is continuously compared to a particular register, the compare register. Instead of a continuous ramp, we have a digital counter. Instead of a comparator, we have a digital comparator. This is performed by the timer counter unit in PWM mode. When the counter is larger than the compare register, the output will be low. When the counter overflows, the output is set high. In this way, the sampling time or period is the time between two overflows. Therefore, the sampling time is the maximum counter value plus 1 multiplied by the counter clock period. In other words, the sample rate is the counter clock divided by the maximum value plus 1. Since the maximum timer clock frequency is 16 MHz, at 8 bits we have about 63 kilosamples per second. This is enough for our application, but we want 16 bits. At 16 bits, that would result in only 244 Hz, which is totally useless. However, we can play with math. Instead of directly generating a 16-bit value, we can observe that we can write any number as a sum of two factors. In particular, we can achieve a 16-bit number by considering the upper and lower 8 bits. Then, we will sum these factors by multiplying them with different weights. In our case, we split the 16-bit sample in the high and lower parts, and for each part we create an 8-bit PWM signal. After that, we sum the two signals with different weights. To do this, we need two precision resistors, one being 256 times the other. In our website, you will find all the details. After the two PWM signals have been summed, we use a simple filter and an op-amp to drive the earphone. In our program, we used a phase-correct PWM. In fact, considering a single-slope PWM, you may notice that the center of all the generated pulses is not evenly spaced. This will reduce the audio quality. To avoid this, we use a dual-slope counter. In this way, the center of each pulse will be always placed at a constant interval. The drawback of this technique is that the number of counts almost doubles, and the new sampling frequency is now about half the previous value. Before actually dealing with the program, we need a further consideration. The audio samples are read at a frequency which is many hundreds of kilobytes per second. They are instead generated at a much lower frequency using an interrupt, which is called with frequency corresponding to the sample rate. However, the synchronization between the SD card read operation and the sample playback would be difficult. Therefore, we use a technique known as double buffering. From one buffer, we send the samples to the PWM units. On the other buffer, we load the next data from the SD card. When we have finished sending all the samples to the PWM units, new data will be already present in the other buffer, as the SD card has a very high transfer rate. At this point, we just swap the two buffers and we can repeat the process again. In this way, we do not have to worry too much about synchronization. The size of the buffer is one sector, therefore each buffer can store at most 256 16-bit samples. Now everything is ready. From the hardware viewpoint, we used again a prototyping board to create a pass-through shield. For that purpose, we used long wire female strip lines. Soldering the circuit has no special issues, and it can be performed in less than 1 hour. The program is simple. After initializing the timer that determines the sample rate, we jump to the loop. In the loop, we open the audio file, then we initially fill buffer 1 and we enter another loop. There, we wait until all the audio samples have been sent from the first buffer to the PWM units. During the audio playback, the other buffer is filled with new samples loaded from the SD card. After buffer 1 has sent all of its data to the PWM units, we swap the functions of the two buffers. Now we load into buffer 1 the next audio data, while samples are being sent out from buffer 2. Here we wait again, and we repeat the procedure by swapping the buffer functions each time. The loop ends when we reach the end of the file. The interrupt routine is simple. We output the odd bytes in one PWM channel and the even bytes in another PWM channel. Each time we also check if there are no samples left. In that case, we notify it to the main loop by setting to 1 the volatile variable named gReadRequest. Finally, everything is ready and we just need a 20 kilosamples per second single channel audio. To do this, choose your audio file and use Audacity to convert it to a 20 kilosamples per second 16 bits single channel audio file in RAW format. Then put the file on the SD card and program the Arduino. After that, remove the power and put the jumper to avoid contention on the USART. Then insert the SD card and the two shields and connect the headphone or some amplified speakers using the jack connector. After that, apply power and you should hear your audio. Now there is still something more to tell you. For our final application, we need a 20 kilosamples per second audio. However, with the 8-bit timers, we can only generate a very limited number of sample rate values. The only one which is not completely useless is achieved when the input frequency is the maximum value, i.e. 16 MHz. With this frequency, we can achieve about 30 kilosamples per second. In other words, we are updating the compare register at 20 kHz, but the PWM is running at a different frequency, about 30 kHz. As you can see, the generated output signal will differ from the original one. The difference is actually an additional noise, which affects the signal quality. In our website we showed two solutions. In the first one, we actually ignored the problem, for sake of simplicity. However, the signal quality will be poor. In the second one, we use timer 1, which allows for a finer adjustment of the period, and it yields the best quality. However, we will be forced to use the off-grid IOH connector. That's all for this episode. The next part will be the last one of this series. We will finally play a video with audio. This is not trivial, because the headroom left is very limited, and a good optimization is mandatory. For more information and to download everything for this project, visit next-hack.com. Be free to comment, like, share and subscribe to this channel. Thanks for watching. What's your next hack?